questions do you have? Yes.
I took like all my homework this week. Can you just go over like the Bernoulli part?
The which part? The Bernoulli. Okay. Yeah. 2.5. Pardon me. 15, you said?
Yeah.
Okay. So we got x dy dx plus y equals 1 over y squared. That one? All right. So, if I move this, if I multiply everything by y squared, I'd see xy squared dy dx plus a y cubed equals 1. So this right here is what I would let my u equal. And so then I'll call it just a u prime would be 3y squared y prime. And so I see the y squared y prime there. So for that, we'll put in 1/3 u prime plus u equals 1. And then from there, we can do what we typically do for first order. Yeah, the idea is that for these Bernoullis, you should see kind of like what you do for u substitution, right? You should see a function and its derivative, except you may have to adjust for a constant. And so in this case, there's where we're adjusting for that constant is that 1/3. Yeah. And then at that point, it should be like every other first order linear equation that we solve. Say that again?
You can leave the x on the left side instead of moving it.
Well, you can leave it when you do your as you do your substitution. You'll want to throw it to the right to figure out what you want to make for your substitution for your integrating factor. You can move it first or move it second. It doesn't matter. I was just trying to figure out what the substitution had to be. But you're exactly right. At this point, you would want to rewrite this as 3 over x u equals 1 over x like that. And then figure out your integrating factor from that coefficient. This should be 3 over x over here too. I gotta move the 3 to the other side as well. That okay? Other questions at all? Squeaked a little bit. Other questions at all? Euler's method still makes sense, okay? With the approximations, being able to go through those. Again, I imagine on the exam I'll have a problem where you'll need to use Euler's method to go through a couple of steps. Make sure you can do that with a calculator. It's not too bad, right? You're just using a tangent line, moving a little bit, recalculating your derivative, moving a little bit, recalculating your derivative, moving a little bit. I'm not going to make you do a whole bunch of steps. If you can do 2 or 3, you can do 10. It's dumb to try to do 10 steps by hand. It'd be a waste of everyone's time. If you want 10 steps, do it on the computer. All right. Well, let's move on then to chapter 4. And we've talked about first order differential equations fairly extensively in chapter 2, where we talked about, being able to do separation of variables, being able to recognize first order linear, being able to recognize exact, and doing some substitution ideas, right? And then we also did that approximation method. So that's what we have so far. I'll just write that down for a summary. So far, we've had first order equations. I figure it's probably a good idea to just write this down since we have a test next week, right? Okay. First order equations. We've talked about separable. Oops, if I can spell separable, that would be helpful. We talked about linear. We talked about exact. We talked about substitution methods. In particular, we focused on homogeneous and Bernoulli. And if I could spell today, holy cow. And Bernoulli, the example that Emily asked about was Bernoulli, right? That's what we've talked about so far as methods goes. And then we had our first approximation method was Euler's method. I guess in some sense that it was technically our second approximation method. Our first one was draw a slope field and try to guess what the solution looked like. Right. But this was all of chapter 2, right? We talked briefly about what they talk about in chapter 3 last time, just to give you a taste of why we care about differential equations in general and first order differential equations in particular from the modeling that we did. Section 3.1 was linear modeling and 3.2 was nonlinear modeling. Very, 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 very important. Not much I'm going to do on the testing side of that for modeling. Again, the point of this class is to introduce you to methods of how to solve these things, give you a taste of how to set things up. In your applications of these things, you'll be doing the flip of that, getting them set up, figuring out how to set things up, and then probably using your computer to give you an approximation for what the solution looks like. Okay. So, I'm not saying that modeling is unimportant, because that's the exact opposite of what I'm saying. Modeling is exceptionally important. It's the whole reason why you take this class. But the point of this particular class is to solve things. Okay. Later on in the semester, we will talk about methods for approximation, which will even be more applied to what you'll be doing in practice. Okay. So later on, we'll talk about using power series to give us solutions for differential equations. Power series help you get polynomial approximations to functions, and so you'll use the power series, chop it off someplace, and do a solution that way. And other solution methods that, for lack of a better word, I'll say extrapolate on Euler's method. Other ways to try to kind of model where the slope is going. And both of those types of methods pop up when you get to partial differential equations, which really started to get into more applied things. Talk about heat equation, wave equation, and those kinds of things from physics, for example, and engineering. So, anyway, let's go on then. We've talked about first order equations rather extensively. So in chapter 4, we're going to talk about higher order differential equations. Most of the time in chapter 4, we will focus on linear equations because they have a nice theory that's developed along with them. And that's exactly what section 4.1 talks about, is the theory of linear equations. Pardon me. Goodness. So we will talk about in this chapter what's nice about linear equations and give us some different methods of solving things. Okay. We will see some similarities with the theory of linear equations for differential equations with when you talk about solving linear systems of linear equations, if you will, in linear algebra. Okay. So we'll see some similarities of those things. All right, but to start this off, let's just talk about what we mean by a linear differential equation. We've already mentioned this, but just to write it down again, we can have, I'll write it with the prime notation. We'll have some function and n of its derivatives. I'm going to fill in some gaps. This is why I'm leaving gaps, by the way. All right, so we've got some function y, and I've got n of its derivatives. And we've already talked about that. That means we have an nth order differential equation, right? In this particular chapter, we're going to talk about, in this particular section, we're talking about linear equations. So notice the way I've written this, I've got y, y prime, and so on. None of them are raised to any powers. None are inside the arguments of any function. We're not dividing by any of them. We're not multiplying any two of them together, right? That's what we mean by linear, right? Same definition we've had before, okay? To these, we'll put some coefficient functions on there. We're going to change these coefficient functions in different scenarios, but for right now, since it's a linear equation, these coefficient functions can't have any y's in them, right? So we'll write these as, say, an a sub n of x, an a sub n minus 1 of x, an a1 of x, an a sub 0 of x, and some g of x on the right-hand side. So this is what we mean as by an nth order linear differential equation. That's an n minus 1. It looks really, really bad as a subscript here. N minus 1. You try to make the subscripts match the order of derivative. It looked like I wrote an M. At least I thought it looked like I wrote an M. All right. So that's all we mean by an nth order linear differential equation. Many times, especially in practice, you try to solve what's referred to as an initial value problem. We've seen initial value problems already. For an initial value problem, for an nth order linear differential equation, we need a certain number of conditions to be able to find a unique solution. And we'll write the theorem down in a minute. We're not going to prove the theorem that's beyond what we want to do in this particular class. But let's think about this. And I said we're going to try to tie some of this to linear algebra. Okay. If I have a function and n of its derivatives, I probably need to know n pieces of information when I'm done. Okay. So when we have an initial value problem, and we've already abbreviated this as IVP, so I will continue to abbreviate it as IVP. I wanted to write it out. I probably need to find n pieces of information when I'm done to be able to figure out the constants. In first order linear differential equations, in first order equations in general, we always had an arbitrary constant that would pop up. So we needed one condition, right? For an initial value problem. But in this case, we probably have something going on. If you think about like an object in motion, you probably know where it is and what its velocity is. That's two pieces of information, right? As an example. All right, so for an initial value problem, here's what makes it an initial value problem. I know what happens initially. So I plug in an initial x, I get out an initial y. But I also know information about the derivative at the same x value. I know something about the second derivative at the same value. all the way to the n minus first derivative at the same value. So just to write this off to the side, notice that the x naught is the same value for all the conditions. Okay, that is an important piece of the puzzle for an initial value problem. Okay, it has to be the same x naught that goes into each of those. Now let's think. I kind of glossed over it a little bit. Let's see if we can think about a little bit more about why I need these many pieces of information. For looking at, if you think about this in terms of kind of solving a system of equations, or just solving an equation of several variables in particular, notice that if I'm looking at the way this is written, if I think about just kind of picking values for the y's, don't worry about them just thinking about them as functions, but think about this as different variables. So think about it as a y naught, a y1, a y2, and so on down the line. I get to pick whatever I want for the y. I can pick whatever I want for y prime, all the way across until I get to, I can pick whatever I want for yn minus 1. But once I have those values, the yn is determined, right? Does that make sense? One of them depends on the rest. And if you think about that in that terms of that normal form that we wrote before, right? We put the highest order derivative on the left-hand side and everything else on the right-hand side. It's the same kind of concept, right? So it kind of gives you a little bit more information about why we need all of these pieces of information, but I don't need one for the last because it's determined by the other ones. That kind of makes it a little bit more sense, kind of give a little more insight on what's going on. All right. So this is what we mean by initial value problem, okay? Again, you can see why this might make sense in applications. You've got some setup of how things interact with each other, and you've got some starting point, and you want to see what happens, right? What happens is I change, I don't know what you might want to change. You've got some populations, you've got some initial population of something that's going on somewhere, and you have some sort maybe it's a predator-prey model, and so you want to see what happens over time, but you know how much of each population is there to start with. That's not an initial value problem, that's a boundary value problem, which we'll talk about here in a minute. But you can think about why you might want to know these things. About you've got a setup about how things interact with each other, about how they change, and you've got an initial starting point, and you want to see what goes on from there. Okay, all right. Why do we care about all of this? Well, it turns out, as a theorem, or since I abbreviate theorem that way, it looks like it's a thumb. Okay, as a theorem, if all of your a sub I of x and your g of x are continuous on an interval I, then, pardon me, there exists a unique function y of x that solves the initial value problem. Missed one small little piece. My x naught needs to be in the interval. Sorry. I just wrote some arbitrary interval. It needs to be an interval that contains the x naught. Now, there are some details in there. This interval needs to be an open interval that contains the x naught. I probably really should have said something about it being centered at the x naught. I'm not going to get into much into the weeds. Boundaries are hard. I think I've mentioned that before. We'll see a case here or two today to talk about why boundaries are hard. Okay, so I would want an open interval around my x naught. I need open intervals anyway to talk about continuity, because remember from calculus, when you talk about continuity, you have to do continuity with limits. Limits are, and they have to come from both sides. That's why I need open interval. Okay, they call it hand waving in that. I'm just kind of talking around it. Okay, rather than giving all the individual details, because you don't need to know the individual details. You know what continuity means from a general sense. You know what an interval is, right? Okay. Just know that it needs to be nice in some region around this x naught. If it's nice, then you get a nice solution. That's the crux of the matter. If you want more theory behind it, take a higher level differential equation course when you go to grad school. Okay. If neither of those two things interest you, then you can ignore what I just said. Okay. All right. That's the important part. This really does have a unique solution. Okay. We're not going to prove that. That's way beyond the scope of this course. There used to be a professor here when I went to school here, 30 years ago. God, that's a long time ago. Who used to say, believe it or flunk. So believe the theorem or flunk. Okay, so you got those are your two choices. All right. Anyway, what do we mean by a boundary value problem then? Well, rather than trying to do this in a general sense, let's talk about what we could possibly mean for a boundary value problem for a second order differential equation. First order differential equation, there is no difference between initial value and boundary value. Why? Well, for a first order differential equation, how many arbitrary constants did you ever come up with? One. So you only ever needed one equation. So initial value problem and boundary value problem are exactly the same thing for first order differential equation. Okay? But let's talk about it as a second order differential equation. If it's second order, then you've got y double prime and some function multiplied by it, because we're doing linear differential equations here. You've got some y prime, some function multiplied by it, some y, some function multiplied by it, and then some other function here. All right, so for a boundary value problem, and we will abbreviate it in the way that you probably think we would abbreviate it. For a boundary value problem, we still need the same the same number of conditions to be able to solve for arbitrary constants. First order equation gives you one arbitrary constant if you don't have a condition. A second order equation should probably give you how many? Two, right? So we'll need two conditions. If it's an initial value problem, those two conditions have to be function and first derivative at the same point, right? Boundary value problems are the other possibilities, okay? You could talk about the function at 2 points. Oops, at 2 points, and I wrote the same point again. It could be the function at x naught is equal to y naught, and the function at x1 is equal to y1. You could have the function is y naught, and the derivative of function at some other point is y1. Telling you about the function value at x naught, but the derivative of the function at x1. You could go the other way around, of course. And then the fourth one is, of course, I could talk about the derivative of the function at 2 points. Those are all examples of boundary value problems. And depending on the type of boundary conditions you have, you get a Dirichlet type of problem or a von Neumann type of problem. Not that you need to know that for me. But there's different names associated with the different types of boundary value problems that you can come across. Okay? All right, so again, trying to connect this to linear algebra. In the original initial value problem, we said that assuming we have certain conditions met, we always get a unique solution, right? There's one, and it always exists, okay? But in general, for your theory of linear equations from linear algebra, what are your possibilities for solving a system of linear equations? Well, how many solutions can you possibly get? Yeah, 0, 1, or infinitely many, right? Those are the possibilities, correct? And that's exactly what's possible for boundary value problems, okay? So for boundary value problems, you might get one, might get none. You might get no solution. You might get one solution. You might get infinitely many solutions. Let's do an easy example why. Okay? Let's just start with that second order differential equation. Can you tell me two functions that satisfy that differential equation? It should be two functions that you know that are the opposite of their second derivatives. Sine and cosine, right? Now, we're going to talk about this in a minute, but that's referred to as a fundamental set for this differential equation. If you've had linear algebra, the word fundamental set really just means basis. Okay? What a fundamental set means is that I can write every solution to this particular differential equation, and we're going to give this type of differential equation a name here in a second, but I can write pardon me, sorry. I can write every single solution to that differential equation as a linear combination of sine and cosine. Okay? All right. You can believe me now, and we'll actually give a little bit more reason for why that's true here in a bit. Okay? All right. If you remember trig, I know it's been a while, this type of function is referred to as a sinusoid. You may not have heard that word. All that means is that its graph will look like a sine function. I can actually, in that form, I can rewrite this function as some transformation of the sine function. Okay? I can write it as a constant times sine of some period and a shift horizontally plus a shift vertically. Okay? That's what a sinusoid means. It just means its graph looks like a sine function. Okay? If you want to play around with it, just change the constant C1 and C2 and see that all the graphs will look like a sine function. Or a cosine function, but you just call it a sinusoid. Why do I care? Okay? The important part of why I care in this case is the fact that notice that this thing is going to definitely start repeating every 2 pi, right? So if I think about something that's going to repeat every 2 pi, it's going to hit the same y value all the way across at 2 pi, right? So for example, if I say, I look at the boundary value problem where I say that y of 0 equals y of 2 pi equals 0, say that was my boundary value problem to start with. Well, look what system of equations you would get if you plug these in over here. If I have y of 0 equals 0, that tells me I have C1 is 0, doesn't it? Agree with that? And if I have y of 2 pi equals 0, that also tells me that, again, C1 equals 0. Did that tell me anything about C2? No. Didn't tell me squat about C2, right? So C2 can be anything. So I get infinitely many solutions in that case. Okay? So there's an example of a boundary value problem that has infinitely many solutions. And if you think about it, why did I choose 0 and 2 pi? Well, I made it match the period, right? I already know that if y of 0 is 0 and the period is 2 pi, y of 2 pi has to be 0. Right? Without a doubt. Right? So there's an example of a boundary value problem that has infinitely many solutions. Can you tweak this boundary value problem so that it has no solutions? Using the same 2x values that I put up there, can you tweak this boundary value problem so that you have no solutions? I probably wouldn't have asked the question if the answer weren't yes, right? So what if I had y of 0 equals 0 and y of 2 pi equals what? Do you think we could do? Think about what I just said a minute ago. If I know y of 0 has to be 0, then if it's periodic with period 2 pi, y of 2 pi also has to be 0. So if I said the boundary value of the boundary value problem said y of 2 pi equals 1, am I going to get a solution? No. So this would have no solution. And that's just playing around with periodicity of the function. That's a fun word to say. That's just playing around with the fact that it's periodic, right? You can come up with different examples for different types of functions where you'll get no solution or infinitely many. I can make exactly one solution by tweaking the problem slightly. I can say y of 0 equals 0, y of pi over 2 equals 1. These two things together will tell you that C1 equals 0 and C2 equals 1. And that gives me a unique solution. It's just the sine function. Okay. So this gives you one solution. All right. Again, like I said, we could do this with a very straightforward example. I do need a second order differential equation to do it. Because again, what did we say at the beginning of this? Well, I've said a lot of things at the beginning of this. What did we say at the beginning? For first order equations, initial value and boundary value problem are exactly the same. So to get this weirdness to start happening, I have to talk about second order so that I can change from an initial value to a boundary value problem. Okay. But again, this is just a really easy example so that we can get started. There are lots of different examples of lots of different differential equations that have exactly the same problem by tweaking the boundary value conditions. Okay. Notice I didn't even play with the boundary value conditions. I could have been talking about the derivatives, right? I didn't even try that. Okay. I mean, I could do that pretty easy as well. I could say y of 0 equals 0 and y prime of 0, y prime of pi over 2 is 1. And I still have the same problem. I think that works. I feel like that works. Anyway, if it doesn't work, I can tweak it. Okay, you can play around with those things as well. All right. Any questions on that at all? All right. So again, moral of the story, initial value problems, if the differential equation is nice, have unique solutions. Boundary value problems, even if the functions are nice, the differential equation is nice, may have 0, 1, or infinitely many. Okay, that's the moral of the story. All right. Let's start talking about how we solve these things. This is really the point of this course where you start seeing lots of connections between differential equations and linear algebra. Homogeneous equation. In linear algebra, when you talk about a homogeneous system of equations, what are your constants on the right-hand side? 0. Same idea for a homogeneous equation for a linear. For a linear differential equation, we say the equation is homogeneous. I can spell. If that g of x on the right-hand side, remember we wrote the coefficient functions all the way across and it was equal to g of x, that right-hand side is equal to 0. Okay? Okay, so that's what we mean for a linear differential equation. If we write it as that right-hand side is equal to 0. Okay. So a lot of times when we're solving these differential equations, if they're not homogeneous, the first thing we're going to do is solve the homogeneous equation to start with. Let's see why. I know many of you have had linear algebra or are currently in linear algebra. So just to talk briefly about this, remember that you can talk about a system of equations in linear algebra as a matrix multiplication. Remember how to multiply matrices where you take the row and multiply by the column? Okay, you can write it as a system of equations in this form. Okay, if this is not 0, then this is not a homogeneous system. Okay, now let's talk about how I can write the solutions to this thing. If I'll call it x sub h is a solution to the homogeneous system, all right, then what do we have? Well, certainly that means that if I take a times x sub h, that equals 0, right? What we claim from this is that if, I'll call it y sub p, is a solution to, I'll call it y sub p. If y sub p is one solution to ax equals b, then every solution to ax equals b can be written in the form y sub p plus y sub h. I don't know why I started writing y's instead of x's. Sorry. Where y sub h is a solution to ax equals 0. I'm going to let you write that down because I know you're writing it down, but let me just talk about what the implications are. I don't want you to focus a whole heck of a lot on the theory. I'm just talking about the theory to understand why what we do is what we do. Okay? Well, let's talk about this for a second. The claim is that if I have one, then I know what all of them look like. Okay? Let me say that again. If I have one particular solution to the non-homogeneous system, then I know what the form of absolutely every single one of them looks like by solving the homogeneous system. I only have to solve the non-homogeneous system once. Right? I only have to solve it for one function. Okay? That's what this says. Okay? Why is this true? Just to show why this is true, if let's say, I'll just write them as y1 and y2. Let me write it this way. Say I take y1 and y2 and plug them in to my matrix equation, and I get b. Okay, so say a times y1 equals b, and a times y2 equals b. What's that going to equal? Yeah, that's not a trick question. That's 0. Doesn't matter if you know what's going on with the matrix multiplication or not, right? If I know two things equal b and I subtract them, I get 0, right? Nice thing about matrix multiplication is it behaves like regular old scalar multiplication with respect to distributivity, right? I can factor out the a. I said a lot of words to say I can factor out the a. Right? Okay. What's this? It's a solution, isn't it? It's a solution to which system? The homogeneous system, right? We agree? Yeah. I plug in y1 minus y2 into the homogeneous system, I get 0, don't I? So my y2 can be written as, I'll probably say written as y1, that's okay. I can write it as y1 plus, I'll write it as a negative 1 times y1 minus y2. I'll write it that way. Here is, think about it this way now. Here is one particular solution to my non-homogeneous system. I said this was another one, right? How have I written it? Non-homogeneous plus solution of homogeneous. Right? The fact that I put a negative 1 in front doesn't really matter, because I can factor out the minus 1 out in front here and I still get 0. Okay? So I've written it as particular solution plus homogeneous solution gives me another particular solution, another non-homogeneous solution, if you will. Okay? So this gives us insight into how we're going to break these things up. The whole reason why I wanted to talk about this. That was a table. Okay. I don't expect you to reproduce this argument, okay? But I wanted to go through the argument and tell you why what we're going to do is what we do, okay? I don't have to, once I have a non-homogeneous equation, I don't have to worry about finding all of the particular solutions. I only have to worry about finding one, as long as I know how to find all the homogeneous ones. That's all that says, okay? So what we're going to concentrate on is how to find all the solutions to the homogeneous ones, and then off of that, how to find one particular one. That's going to be our method. Okay? Literally, that's what we're going to do. Okay? All right. So let's see if we can get to that point. To do that, we need to talk about this fundamental set idea. All right? All right. To get to the fundamental set idea, we need to understand the idea of linear independence. Again, if you've seen linear, you know what linear independence is. If you've not seen linear, it's not a huge leap to understand what it means. All we mean is that for something to be linearly independent, just as a particular example, let's say I start with cosine x and sine x. All right, and I have some constant. No. Yeah, I'll just use regular constants here. Yeah, I guess I do want regular constants. Let's start there. Let's just start with that equation. Okay. I don't mean sometimes it's equal to 0. What I mean by this now is, can I find literal constants that will make that 0 no matter what you plug in for x? Is it possible to find C1 and C2 to give me 0 all the time? Well, what's one solution? Definitely. Yeah, use them both 0, right? Is there any other ones? So again, think about it. I've got a sine function that looks like this and a cosine function that looks almost the same, but it's shifted, right? Can I find two constants where I add those two things together and get me a flat line all the time? Because that's what a flat line has to be, right? Is if it's going to be 0 all the time, it has to be flat. Is it going to be possible for sine and cosine? No, it's not. Okay? So that's what we mean by linear independence. If I know that this is true, then this implies that my C1 and my C2 both have to be 0. That's what linear independence means. So I'll write out the longer definition here. We say, I'll call them F1, F2, out to Fn, are linearly independent if whenever C1 F1 plus C2 F2 at the Cn Fn equals 0, we have that all of the C's are 0. They literally do not depend on each other. That's what that means. Okay? All right. So what we're looking for when we solve homogeneous linear differential equations, we want to find, so a goal for a homogeneous equation of order n, find a set of n linearly independent functions or solutions for the equation. All right. A little bit of theory that I'm not going to write down, so you don't have to write it down. Okay. But generally speaking, from a linear algebra standpoint, when you have a set of linearly independent vectors, when you do all of the linear combinations, meaning taking that constant times 1 plus a constant times another and so on down the line, when you form all the set of linear combinations of those vectors, you get what's referred to as a subspace of some bigger space. Okay, it's called the span. Okay? Set of all linear combinations is called a span. If you've got a linearly independent set to start with, I can write every linear combination as unique. Okay, what I mean by that is, if you've taken physics, with i's, j's, and k's. If I write a vector in terms of I, j, and k, there's only one way to write it. Literally, only way to do it, right? If I have the vector 1, 2, 3, that's 1i plus 2j plus 3k. I can't write it as 7i plus 9j minus 7k, right? There's one way to write it. We refer to that as a basis for the vector space. When it's linearly independent and it spans, it's called a basis. It generates everything, okay? All right, where am I going with this? Okay? When we have let me take one more step before I get there. Again, from linear algebra, when you have a basis for a space, the dimension of that space is the number of vectors that you need to generate it as a basis. Okay? For our purposes, the size of our space is going to be the order of the differential equation. Okay? Think about when we set up that initial value problem, we said that we needed enough conditions to find all of our arbitrary constants. And we had n of those conditions. They started at 0 and went up to n minus 1. We had n conditions. Okay? So when we're finding this set of n linearly independent solutions, that's telling us that that's going to give us a basis for the space of solutions. And we know that we need n of them because the order is n. Okay? That's why this is our goal. Okay? So I know I said a lot of words that you probably don't care about, and that's okay. But I want to tell you where it comes from. I don't like writing things down, at least don't tell me where it comes from. Okay? So again, solutions form a subspace. Why? For homogeneous systems, they form a subspace. Why? Again, if I have two solutions, I can add them together and get a new solution. I can multiply by a constant, get a new solution. It's the fact that they're equal to 0, right? Okay? It's the fact that they're equal to 0. If I add two things and plug it in, I get 0, I still get 0 when I add them together, right? Or if I plug something in, I get 0, and if I multiply by a constant, I still get 0. Because derivatives behave nicely with those two operations. Okay. So, again, I want to find this set of solutions because that's the set of all linear combinations will generate all of them. And I know I need n of them because it's nth order. Okay. And I'm going to stop there as far as talking about theory. Okay. All right. So, given a function, given a set of functions, how do we determine if a set of functions is linearly independent? Right. We do this with something that was referred to as the Wronskian. Isn't that a fun name? Okay. All right. So rather than me giving you a long-winded definition of what the Wronskian is, let's do a specific example. Let's see. Let me just ask it this way: R cosine of x, and let's say y1 equals cosine of x, and y2 equals sine of x, linearly independent. We already mentioned that they are, but let's talk about how we compute the Wronskians to do that. So what the Wronskian really is it's just a determinant, okay? As a numeric check, again, if you've had linear, one of the numeric checks for being able to tell if a matrix is invertible is if its determinant is not 0, right? That's one of our numeric checks. If you are just now taking linear, you'll discover the same thing, okay? But the idea is that the determinant is not 0 tells you that it's invertible. And if it's invertible, then you get exactly one solution. And then if it's exactly one solution, then you also know that the columns form a basis and all of that good stuff. Everything is connected that way. If you had me for linear, you learned like 20 different ways to say that a matrix is invertible. Right? I see some nodding heads from people who had linear from me. Okay, you learn about 20 to 25 different ways to say, hey, the matrix is invertible. All says the same thing. Anyway, so let's talk about how we take a determinant for a Wronskian. So it's really straightforward. Okay, so the first thing you're going to do to form your determinant is your first row is just the functions that you have. Okay, we only have two functions here. So I have a cosine x and a sine x. That's row 1. Now, how many columns did we get from row 1? 2. Good. That wasn't a trick question, okay? To be able to take a determinant of a matrix, it has to be square. So if I have 2 columns, I have to have 2 rows, okay? I get the second row by taking the derivative of the functions. And if I have 3 columns, I'll take a second derivative to get to the third row. If I have 4 columns, I'll take a third derivative to get to the fourth row, and so on down the line. Okay? So here I'll get negative sine x and cosine x. Just differentiate down. Okay? The reason why we use this determinant is because determinants help us determine invertibility, which tells us about linear independence and all that stuff. That's why we're using a determinant. Okay? This determinant is pretty easy because if it's a 2 by 2, remember you multiply this way, multiply that way, and subtract them. So this will be cosine squared x minus a negative sine squared x. That's sine squared plus cosine squared, which gives me 1. Now, here's the thing about the Wronskian. Not can it be 0 for some particular value of x. If it's not going to be linearly independent, then it has to be 0 for all x. As long as that's not a 0 that when you're done, you're good. Okay? The important part here is this is not equal to 0. Okay? So that set is linear. So the answer to our question before is yes. Okay? Let's do a 3 by 3 example. I'm not ever going to make you do anything more than 3 by 3, by the way. Okay? All right. So let's say you have y1 is 1, y2 is x, and y3 is e to the x. I'll use W to denote the Wronskian. Again, to create your determinant, your functions go on the first row. Functions on the first row. Differentiate down your columns until you get a square matrix. Okay? What's the derivative of 1? 0. Derivative of 0 is 0. Since I have 3 functions, I need 3 rows. So I know I'm done here. Okay? Derivative of x, 1. Derivative of 1, 0. Okay? Derivative of e to the x, e to the x, derivative of e to the x, e to the x. Okay? That would be that's the determinant we need to take. Now there's different tricks that you can do for taking determinants. This one's the easy one. Do you see why this matrix might be called triangular? I've got zeros down here in this lower triangle. Anytime you have a triangular matrix, how can you take the determinant? Just multiply down the diagonal. So the determinant here is 1 times 1 times e to the x gives me e to the x. Is that equal to 0 all the time? No, it says e to the x, right? That's not a 0, correct? Now, turns out e to the x is never 0, but that's not the point. The function can equal 0 sometimes. For them not to be linearly independent, it literally has to say equals 0. Everything has to cancel out, okay? This is not 0, so these are linearly independent. That's how we check. That's what the Wronskian does for us. Okay? All right. So far, so good? I know, lots of theory today, which isn't exceptionally helpful for you, but that's okay. All right. Good news is I think we're out of theory that we need. The last piece is that, just to write down what I mentioned before, for a homogeneous linear differential equation, a fundamental set F1, F2, up to Fn. I should have put the order. A fundamental set F1 out to Fn generates all solutions for the nth order equation. So we typically write it as a general solution. I'll write it as y sub h in this case. Will be C1 F1 plus C2 F2 out to Cn Fn. Fundamental set just is basis. It's n functions that are linearly independent for the nth order differential equation. Okay. All right, so again, just to emphasize, our goal when we solve these equations will be to find fundamental set for the homogeneous system and then a particular solution if we have a non-homogeneous equation. I said system on that equation. Okay. All right, so let's start trying to do that so that I can stop talking about theory because I'm sure you're sick of it. It's the part that I love. It's the part that students typically hate. That's why I'm a mathematician. All right, so first one's called reduction of order. Rather than making a long-winded lecture, let's just talk about what we mean by this. So this is number 2 in section 4.2. They start with the equation y double prime plus 2y prime plus y equals 0. Order of this equation? Second. Is it linear? Yes. Is it homogeneous? Yes. So if we're looking for a fundamental set for this linear difference, homogeneous linear differential equation, how many functions should be in the fundamental set? 2, right? There should be 2, correct? Okay. In reduction of order, the idea is that you have one, you find the other. Okay, so they give you one, you try to find the other. Okay, so we know that the function y equals x e to the negative x is one solution. Okay. They tell you this. You're not finding it here. They tell you that it is one. Okay? All right. So we need to go hunting for the other. Okay? Now, again, fundamental set means linearly independent, right? That's what fundamental set means. So can my other one that I'm looking for simply just be a constant times this? No. Okay? So this is the idea. We're going to consider, it doesn't really matter what I call it. Let's use the next one. Y2 is some function of x times y1. It can't be a constant. It has to be some function of x times y1, right? But we don't know what it is. Okay? I'll not put the of x in there. Okay? We want this to be a solution. That's the whole point, right? We want this to be a solution. So if I plug it in, it has to work, right? So we want ux e to the negative x double prime plus 2 times ux e to the negative x prime plus ux e to the negative x to equal 0. That's what we want, right? We agree? It needs to be a solution. We're trying to find a second one. So when we plug it in, it needs to work. Okay? Problem that may not have been the best one to do to start with because I got a nasty product of 3 functions to go with because I need to take derivatives here, don't I? Okay. Pardon me. So let's see. Let's do this one first because if I differentiate this one, then I can differentiate it again for the second one. Okay, let's just do this off to the side. I want the derivative of ux e to the minus x prime. That'll certainly be u prime x e to the negative x, right? Derivative of the first. And I don't know what u is, so I have to write it as u prime plus u times, and then I do the derivative here. That'll be e to the minus x e to the minus x using a product rule there. Do you agree with that? I did it quickly, but does that make sense? Should have used a different one to start with, but that's okay. I thought number 2 pulling out of the book would be, not as much algebra to have to do. That's okay. All right. So this part here will go in over here. Okay. So we'll have plus 2 times all of that mess. Now I have to do the derivative again, don't I? So I tried to leave some room on this side. Oops. This is what we're differentiating now, correct? I just underlined this part right here. Yeah, okay. So that's gonna. I need a derivative of that over here. So this will be looking. Oh, for heaven's sake! This will be looking at the first term. We'll have a u double prime x e to the minus x, and then plus u prime times. I should have left myself a little bit more room. E to the minus x e to the minus x. It looks like the derivative we just took is just we're using u prime instead of u. Right? The next part's going to be a, what? U prime e to the minus x minus u e to the minus x. And then the last part is the function that we already differentiated once. So the last part will be minus u prime x e to the minus x minus u e to the minus x. And it'll be a plus ux e to the minus x. I know, it's a lot to keep track of. Hopefully it'll get better here in a second. Again, that last term was literally what we just differentiated, so I just wrote it down again, right? That ux e to the minus x, what we just took the derivative of, it just has a minus in front of it, so it flipped all the sides. All right, here's where the idea of reduction of order comes from. We started with a second order differential equation. Reduction of order would imply that we need to go down one, right? To a first order. That means that anything that just has a u all by itself better go away. Okay? Otherwise, we didn't reduce the order. And we'll see why it reduces the order here in a second. But at this point, after we've made the substitution, assuming we've done everything correctly, all the u's should go away. Okay? Do they? Well, let's see. Here's a u e to the x. Here's a u e to the x. Here's a u e to the x. Do those cancel? -1, -1, +2. Those cancel, don't they? Yeah? Where else do we have a u? Plus ux e to the x, plus ux e to the x, -2 ux e to the x. Those also go away, don't they? All right, so that goes away, 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 that goes away. I know it was ugly to start, but a lot of things just went away, right? We agree? Okay, what's left? U double prime x e to the minus x. Everything else that's left should have a u prime in it. How many do we have? Let's start with just the u prime e to the x's pieces. Here's a u prime e to the minus x. Here's a u prime e to the minus x. There's two of them, right? Here's one, here's another. Okay. So we should have a plus 2u prime e to the minus x. And then let's do the minus x e to the minus x pieces. There's a -1. There's a -1. There's a +2. Right? -1, -1, +2. Those also all kill each other, don't they? Okay? So all we're left with is equals 0. Oops. I know it was ugly to start. That's much better. Right? I could even make it better. What can I divide both sides by? And make it even look a little bit nicer. E to the negative x, that's never 0, so I don't have to worry about anything, right? So I can get u double prime x plus 2u prime equals 0. Now I've made a really straightforward differential equation to solve, haven't I? Now here's why it's called reduction of order. Obviously, this is still second order, but are there any u's all by themselves? No. So if we make a substitution here, I'm going to call it w, just so I don't have to have a u that looks like a v that looks like a u. Then I get w prime x plus 2w equals 0. What kind of equation do we have now? Yeah, it's separable or it's first order linear, either or, right? You take your pick, doesn't matter, right? We agree? Okay. As a matter of fact, pardon me. Let's just do it as separable. This would be w prime over w equals 2 over x. Negative 2 over x. So you'd have log of w equals negative 2 log of x. Plus a constant. Yeah. And then this would be w equals some constant times x to the negative 2. If I move the negative 2 up and do e to both sides. Yeah, should be right. Yeah, that's right. Okay. Sorry, I was convincing myself it was right. Okay. Now, what was W equal to? I know we're out of time. What was W equal to? U prime. By the way, I guess I put the arbitrary constant in here. I don't really need the constant here to start with because it's going to get absorbed by something else. Sorry about that. We don't need this C here yet. We're just trying to find another solution for our fundamental set. So I don't need the plus C. Okay. So U prime is equal to x to the negative 2, which tells me that U must have been negative 1 over x, doing the antiderivative both sides. Right? So what was my y2 then? My y2 is u x e to the negative x. Right? That was where we started. So y2, I can do negative e to the negative x. Do I need the negative sign? If I'm just looking for a fundamental set, does the constant matter? I don't have to worry about the constant. The negative doesn't matter. Or I could just do y2 is e to the negative x. That was long, wasn't it? Okay. So that's how reduction of order works. Every single reduction of order problem works that way. Okay. All right. So let me give you a couple of problems to work on. I know I'm 2 minutes late. Sorry. 4.1, 3, 13, 15, 21, 25, 33, 4.2, 3, 9, 13, 17, 21. Okay. All right. So next time we will talk about how do we find these functions without having to try this reduction of order stuff. Okay. Your exam for next Thursday will only go through 4.2. We will cover new stuff on Tuesday, but it will only go through 4.2. Okay. All right. Have a good one. Sorry about the couple minutes late.